A lot of traumatic things happened to the early Earth. Among the earliest, a Mars-sized asteroid crashed into the Earth, and the molten guts that got spit out turned into our moon. But even after life evolved and the geological activity of the Earth calmed down a little bit, even after life evolved, at different points, the existence of life on Earth has been punctured, and species have there have been mass extinctions of species. Of all of the different mass extinctions, perhaps the biggest is one that occurred because of radicals. A microbe called cyanobacteria, and that's this stalk that's getting eaten in this video. A microbe called cyanobacteria started releasing radicals into the atmosphere. Radicals started accumulating in the atmosphere in the tons. We know that radicals are very reactive, and so they started ripping stuff apart, tearing electrons away so that their electrons could be paired up. The radicals that they started releasing into the atmosphere, those really dangerous molecules, are still in our atmosphere. In fact, they make up around 20% of our atmosphere. The radical that those cyanobacteria first started releasing into the atmosphere, and that made approximately 99% of species go extinct, one of the most traumatic events in Earth's history, that radical was oxygen. And the event was called the Oxygen Catastrophe. It happened around 2.4 billion years ago. Oxygen, if you draw the structure of molecular oxygen, so you would have been exposed to it already as O2, and if you draw that out, or if you look it up, say, on Wikipedia, they'll usually give you a structure that looks like this. But this is a little misleading, because when you see how oxygen behaves, it does not behave like this molecule here. Rather, it behaves like a di-radical. It behaves as if this pi bond were always broken, and the two electrons in it actually turned in to two radicals, one on each oxygen. So maybe a more accurate depiction of an oxygen molecule would have just a single bond between the oxygens and an unpaired electron on each oxygen. And that makes that oxygen really, really reactive. Now, anytime there's a big catastrophe and a whole bunch of creatures die, they leave behind ecological niches that are as much an opportunity as a graveyard. New species can evolve to fill those empty spaces. New species did evolve, and they were the eukaryotes. Eukaryotes evolved to make use of oxygen. Sure, this is an explosive material, but if it's so energetic and reactive, these creatures, eukaryotes, learned how to use that energy and channel it to increase their growth. And if you've taken biology, then you know that aerobic respiration, the energy that cells get using oxygen, produces way more energy, so much more ATP, than anaerobic respiration. That's when cells try to get energy without using oxygen. So this is a very dangerous molecule. It rips stuff apart. But it can also be very useful because you can get a lot of energy out of it if you're a living thing. And a lot of the adaptations, the differences in eukaryotic organisms, arose to adapt to the presence of oxygen so that they'd be able to use it. For example, the nuclear envelope, the nucleolus, that membrane that protects nuclei that's present in eukaryotes and not in prokaryotes, would have protected DNA from damage done by these oxygen radicals. And mitochondria, which use the oxygen to get more ATP and energy, is another piece of evidence. Now, there's lots of evidence besides that biological evidence for this oxygen catastrophe. One of them are ice cores. People drill miles deep into the ice in Antarctica, and they can tell the composition of the gases that froze with the ice at different points in history based on how deep in the ice core, the gas is found. And you can see where rocks are deposited in gigantic mountains. So, for example, if you go to the Grand Canyon, the deeper you go, you can look at layers of rocks. Those layers of rocks were deposited at previous years in Earth's history. And so you can get a sense of what the atmosphere was like based on what is in each of those layers of rock. And so people have deduced that this great oxygen event, this oxygen catastrophe, occurred and changed the atmosphere of Earth. Now, from a medical perspective, we'll have the opportunity to talk about this and how it relates to free radicals and antioxidants in a future video. But note that it is a good thing that our atmosphere is only around 20% oxygen. It's around 79% nitrogen, which is very stable. A nitrogen molecule has 3 bonds, does not act like a radical at all. That has its own interesting story behind it, but if you put someone in a pure oxygen environment where the air is 100% oxygen, as they do sometimes in hospitals, if someone's dying from carbon monoxide poisoning, where they're not getting enough oxygen, they'll stuff them into a room that has pure oxygen. It causes a lot of damage to a person's body. These radicals tear apart their tissues. Okay. That's a sort of long but hopefully kind of interesting introduction to how oxygen is actually a radical, and we'll see how it uses its radical nature to create fire. And we'll explain what fire is. Fire is a radical reaction using oxygen. Now, the overall reaction you would have been exposed to in general chemistry. It was called combustion at the time. And for combustion, you need oxygen, you need some hydrocarbon, you need heat, those 3 things, and you'll get carbon dioxide and water. This is the carbon dioxide that is released into the atmosphere when we burn gasoline. It's the carbon dioxide also that we exhale. We inhale oxygen, we eat hydrocarbons, and we exhale carbon dioxide. So in our cells, a similar reaction as the reaction we're about to draw happens. But this reaction, So this reaction is combustion, and it creates fire. Okay, how does it create fire? To illustrate this, let's use a simple molecule. The molecule we're going to use is a small hydrocarbon. We'll use, here they're talking about ethane. And actually, ethane. So ethane is 2 carbons. It has all single bonds. And it has a hydrogen here on all of these. So that's ethane. This is our hydrocarbon. So if we had C2H6, for example. Okay. Now, if that goes in the presence of oxygen, oxygen is a diradical. It has those 2 unpaired electrons on either side that are really reactive. Now, the first thing you need is to heat this hydrocarbon up. And as you heat a molecule up, its bonds vibrate faster. We draw bonds as these static stick figure things, but actually they're more like springs. Bonds vibrate back and forth. The atoms come closer and then they get further apart. They vibrate like 2 balls at the end of a spring. They vibrate very fast, around 10 trillion times per second at room temperature. But as you get them hotter and hotter, the springs move faster and faster, and eventually they snap. And if you get this hot enough, this bond vibrates so fast that it snaps, and 1 electron goes on 1 carbon, the other goes on the other carbon. You get homolytic cleavage. So in the presence of heat, you would form 2 carbon radicals. Now, by itself, that wouldn't matter very much. By itself, those radicals could just pair up again, couple again, and you'd end up with your original molecule. You wouldn't have fire. But if oxygen is around, then oxygen can insert itself. We'll focus on one of these. We'll draw the rest of the reaction for just one of these carbon radicals. We'll set the other one aside. The other one is symmetrical to it, and so the process of the reaction would be the same for that. But what happens is the carbon radical contributes 1 electron, the oxygen radical contributes 1 electron, and you form a new bond between the carbon and the oxygen. And by forming that bond, you make sure that the carbon chain is split apart. This will not come back together with the other carbon that it was associated with in that structure before. Oxygen has taken its place. So now you have this bond between the carbon and these oxygens. Now we have an oxygen to oxygen bond which is very unstable. And so that breaks apart. We've seen this already in the case of peroxides. In the presence of heat, that will break apart. And we said heat is part of this reaction. You need heat for this combustion to happen. First, to burst open the carbon chain, and then to break this peroxide here. So what we have after that breaks apart are 2 more radicals. Notice this 1 oxygen is by itself a diradical. It ends up abstracting one of the hydrogens. So it donates 1 electron, it steals 1 electron from the hydrogen. The other electron in this bond goes back onto the carbon. So a hydrogen abstraction. So you end up forming a bond between the hydrogen and the oxygen, and you end up forming a radical on the carbon. Now, almost immediately, this radical pairs up with the neighboring radical, the oxygen there, so you have a coupling reaction. So we form a new bond, a second bond between this carbon and this oxygen. Our other oxygen radical is still bouncing around, very reactive, and it steals another hydrogen. Takes an electron from the hydrogen, the other electron in the bond goes back onto the carbon to create a new radical. So this bond breaks, the hydrogen forms a new bond to that oxygen. We have another radical on the carbon. And notice what we've made, water. That was one of the products of combustion. We saw that up here, one of the products was water, and so we've made that. Notice what the other product is, carbon dioxide. We're working our way there. So another oxygen comes in, another oxygen molecule comes in. Notice that you need oxygen present in order for this to happen. Fires require oxygen. We'll explain where the light from fires comes in a second. One of these radicals donates 1 electron. Oops. So you have a coupling reaction here to form a new bond between the carbon and this oxygen. Just like before, we have this peroxide. That bond quickly breaks in the presence of heat. And just like earlier in this mechanism, we form this radical on the oxygen and a diradical on the other oxygen atom. This other oxygen atom, very reactive, rips off the hydrogen here. So it donates one electron, steals one electron from the hydrogen. We've seen this before. The other electron in this bond goes back on the carbon to create a carbon radical. This bond breaks. We have a new bond between the hydrogen and the oxygen here. This will eventually go on to become another water as it steals a hydrogen from another carbon chain. But here, we form a carbon radical, and almost immediately, this radical pairs up with the radical that we have on the oxygen. And you have carbon dioxide. So that we end up creating carbon dioxide in this reaction and water. So, carbon dioxide and water. This reaction, and then let's first, before we just talk about one last implication of this reaction, let's explain where the light from fire is coming from. What you have here, let's say when you have these radicals, let's say we have these two radicals. This is very high in energy. This is very high in energy. When they come together, it's low in energy. So the radicals are very unstable. You have a lot of energy. Once they bond, there's low energy. Where did the energy go? It's released as light. The light of fire comes from high energy radicals becoming more stable and less energetic. The energy that was there is released as the light. And so wherever you have the light in fire, that's where two radicals combined. And step back and think about this radical reaction for a second. Think about how much human life and energy, how much debate, and how much civilization is going to be affected by this reaction. This is the reaction that happens whenever you burn hydrocarbons. We talked in the last exercise about the hydrocarbons you get from crude oil. Every time you run your car, you're using this reaction. And the carbon dioxide that's released at the very end of this ends up acting as a greenhouse gas to trap heat on Earth's surface. Also, it makes the rain more acidic, as we've discussed in a previous chapter. And so it changes the surface of the Earth. It changes the type of planet we live on, this reaction. And so it's worthwhile, I think, knowing how it works. Ultimately, it's a radical mechanism. You need oxygen, a hydrocarbon, and heat. And to fight fires, you just have to eliminate one of those elements. When people try to fight fires with water, they are trying to get rid of the heat. It's very hard to heat water up. That's one of the reasons why your body uses it as sweat. It's able to absorb a lot of heat before it evaporates. So you can pour water on hydrocarbons and they're not hot anymore, and so they won't homolytically cleave anymore, and so the fire stops. On the other hand, you can remove the oxygen. And that's what the molecules do that are in fire extinguishers. Those molecules are able to create other radicals, and we'll have a chance to talk a little bit more about them in the video that I make on ozone. But those create other radicals that take the place of oxygen so that oxygen won't let this radical reaction continue. Overall, in this reaction, you have heat causing homolytic cleavage, and that initiates a series of radical reactions where oxygen combines with carbon radicals, breaks and then steals hydrogens to create another carbon radical that combines with the oxygen. So the oxygen radical steals a hydrogen, creates a new carbon radical. Oxygen breaks apart, steals another hydrogen, and the two couple again. So this mechanism is one you would want to be able to draw. It's kind of long, but you'll see similarities in what happens. It's really one process that sort of repeats itself throughout. And because of the significance of this in terms of combustion affecting the Earth and how prevalent this reaction is and how important the reaction is, I think it's worth knowing. So that is the explanation for what fire is, how it produces light, what it needs to run, and how you can stop it or quench it.